Swayam Prabha. Digital India. Educated India.
In the last lecture, we started off with microbial growth models, and we'll continue from where we left, a little bit maybe earlier. So we talked about the process of growth and what are the nutrients that are necessary, what are the chemical reactions that happen during growth. And then we started to look at the different kinds of growth models that are there. So if you look at the screen here, so we started off with the Malthusian model, which simply said that Rx is dx dt. And then we went on to look at the logistics model, which tried to propose the second order dependence of on the reaction rate of the substrate, and then we got dx dt is kx times 1 minus beta x, and then the next model was the most important model we looked at, which was the monod growth model. Just a sec. Sorry, I think something skipped here. So we had the monod model to start with, which was mu times s over ks plus s, and then we modified it using the monod growth model, which we call the modified monod model. We added a ks plus s naught term in the denominator, and then we had the Konak model. As you can see over here, what happens in the Konak model is that the Konak model, for the limit of p going to 2, for the case of p going to 2, goes to the monod model. Fine. So this is where we stopped, if I remember. Now, where we'll start today is the values. So if you're doing a monod model, for example, that you have these Ks, the rate constant, and the mu max maximum rate. Okay, and so what we're going to start with today are the values of mu max and Ks for various organisms and substrates. Right. So the first one we look at is Escherichia coli, E. coli, that is. And the growth temperatures that you see over here are the optimum temperatures. As I told you before, that there is a range within which these microorganisms can grow. But then within that range also there is a temperature that is an ideal or optimum temperature. And as we discussed before, what happens here is that for an ideal or optimum temperature, and I talked about this point that, tropical or subtropical countries, you have the growth of these bacteria a lot more than colder countries. The reason being that the optimal temperature, as you can see over here, is ideally suited for a tropical or a subtropical climate. So, excuse me. So, E. coli, for example, it can grow under different kinds of nutrients. So, depending on the nutrient that it is growing in, the mu max and the Ks are going to be different, obviously. Very, very straightforward, because, if you change the substrate, the growth rate is going to change. So, if you look here, for glucose, for example, if the limiting reactant nutrient is glucose, for example, if you're using glucose to grow the bacteria, to grow the microorganisms, then the mu max is 0.8 to 0.14 and the Ks is between 2 to 4. If you're using glycerol to grow E. coli, then the mu max is 0.87, Ks is 2. If you're using lactose, then it's 0.8 and 20, so Ks is much larger over here. And Saccharomyces cerevisiae, which is an yeast, if you're using glucose to grow that, and the mu max is 0.5 to 0.6 and Ks is 25, and this Candida tropicalis, and this if you're growing with glucose, the mu max is 0.5 and Ks varies between 25 and 75. And Klebsiella aerogenes, if you're using glycerol, then mu max is 0.85 and Ks is 0.9. So what you find, what you find is that the mu max, more or less, irrespective of whatever bacteria you're growing or microorganism you're growing and whatever substrate you're using, more or less remains around the same number. Whereas Ks kind of changes, but again the range of Ks for many of these is in around 20s and some of these in the 10s. But again, the order of what I'm trying to say here is that the order of magnitude remains more or less the same. Okay, so the order of magnitude doesn't change too much. It's still in the range of 1 to 100, that order. And then the values of activation energy, and we discussed, if you remember, we had discussed this when we were doing enzymes, the dependence of temperature. So whenever there is a dependence on temperature, there is the effect of activation energy, and that is also related to the question that why a certain temperature is optimal or good to grow a certain microorganism and why other temperatures are not good. right? And then the question of tropical and subtropical climates and all those arise. Because if it's, for example, if these are the temperature ranges, and if the temperatures are too low, then this is an activation energy. Now, the activation energy is required, but the total amount of heat that is generated or required is dependent on temperature. So, if the temperature is very low, for example, that amount of heat would not be generated or required to do that. So, that's why, and this gives you the range for the EAs for the different bacteria. So, most of them, as you see, are grow in this range of 20 to 37. This is 20 to 40, but essentially that is the growth range, and that, as I said again, is a very ideal climate, the subtropical climate. And these numbers are around 13 and 14. This psychrophilic pseudomonad, the temperature range is lower here, and it grows in colder temperatures, and the EA for that is obviously larger, right? Because if the actual temperature is lower, then the EA has to be larger. And there are certain bacteria or virus. For example, the bacteria that we are used to at some points of time, including this time, there's a common cold virus. Okay, so it's so for example, at home your mom will say that you caught a cold. What do you mean by you caught a cold? You didn't catch a cold. Cold is not a thing that you catch. It's a virus that you catch. Okay, so the reason people say this so easily, that you caught a cold, and it kind of becomes a part of our everyday linguistics. But essentially, we are talking about viruses. So when people say that you caught a cold, what they mean is you caught the common cold virus. If you expand that statement, that is what it means. You caught the common cold virus. So it's one of the rare viruses which actually can exist in a colder climate. A lot more than a summer climate. So you won't have the common cold virus during summer or high temperature season, whereas you would have this especially during the cold temperature. So this is one of those. So just like this. So, which grows in 2 to 12, and common cold virus actually grows at temperatures this and much lower than this. Okay. Now, what you're going to look at is essentially the major topic of today is the effect of mass transfer and growth. Now, if you remember, this is exactly how we did the enzyme. So we looked at kinetics of the problem. So we looked at the effect, the reaction aspect of it, and then we looked in immobilized enzymes. We looked at the transport aspect or the mass transfer aspect. And then what you did much of the first half of the semester was the combined effect of mass transfer and reaction, which was, I think, sort of something new. I'm not sure exactly what you did in the last previous courses, but sort of something new as compared to what you might have done in previous courses. You would have done them. There are courses where you would have done mass transfer or transport, and then there are courses where you have done reaction. But in real life, what happens is these two things kind of compete with each other. So reactions and mass transfer either occur in series, okay, or occur parallelly or simultaneously. Okay. So then if you remember, what we did in the last part of the semester was we looked at these several cases where reaction follows mass transfer, and there are cases where reaction occurs simultaneously with mass transfer. And the same thing is actually applicable to growth models. The reason being that growth is essentially a reactive process, right? It's a reactive uptake process. And if you remember, just because in a few days I can go back and show you the reactions over here. For some reason, I think something happened. Anyway, if you remember, I don't have the reactions with me right now, but if you remember, the reactions that we wrote was the reaction of glucose or some kind of carbohydrate and nitrogen with the cell, okay, which resulted in an uptake of carbon, hydrogen, oxygen, and nitrogen to the cell, right? And one of the confusion that you might have, see, for example, what we are doing in the models are we are using two symbols, X and S, okay. So what does X stand for? X stands for the cell, and S stands for the substrate. Okay, so please make a note of that. Don't forget this. So S stands for the substrate. So S is the substrate as a whole. So it could be the nitrogen, it could be the oxygen, it could be the carbon or the hydrogen, but substrate as a whole in general. And X stands for the cell. So essentially, there is a reactive uptake of these substrates by the cell, and the cell grows as a result of it. So there is a reaction aspect of it, but there is a mass transfer aspect of it as well. And why is that? Because the substrate essentially has to overcome some mass transfer limitations or transport limitations to go to the point where the cell can actually uptake it through a reactive process. So exactly like the enzyme thing, that immobilized enzyme thing that we did. And we'll do some few cases today or maybe tomorrow as well. So this is an example that we are looking at here. This is a cell, okay. This inner circle that you see over here is a cell, and the outer circle that you see over here is the liquid film or the boundary layer. Okay. So see what happens essentially, that you this is a cell, and it's a cell is growing in a medium, right? I discussed this in the last lecture, all of it. The cell is growing in a medium, and you might have stirring in the medium, may not have stirring in the medium. You might have stirring. You can use a plate inside the incubator to kind of shake it. So whether you have stirring in the medium or not, there is always going to be a liquid layer, stagnant layer. It's not really a boundary layer, but a stagnant layer, which is similar to a boundary layer. A boundary layer is for a moving system, but even if you have stirring or not stirring, so what happens, because the cell is solid, there is always going to be a stagnant layer of liquid around the cell, right? Is it clear to everybody, or is that something that you agree with? Okay. So then this layer, liquid layer, say, has a thickness of B or something, whatever, delta, let's say. Now, what happens as a result of the presence of this liquid layer is that the substrate has a concentration S0 outside, and the concentration at the interface of the liquid layer and the cell is obviously going to be lower than the concentration outside, okay, which means that there is a concentration gradient in between the bulk and this point. Okay. Now, unlike in the case of the enzyme, we may not actually want to go and solve for the concentration profile of in this liquid layer or stagnant film. The reason being, the stagnant films are typically very thin, and it's probably of not much practical use to actually go and solve for the concentration profile in this. Okay. So what we do is we simply use the concept of a mass transfer coefficient. So what you see over here on the screen, KL times A prime X over rho cell times S0 minus S. Okay, let me explain each little thing. So KL times A prime is the KL is probably the mass transfer coefficient per unit area times this area, and then X over rho cell is the volumetric increase of the increase of the cell volumetric increase. So you divided, say, X is by weight, and you divided by the density, so you get the volume of the cell. So this is KL times A prime would then be per unit volume. Okay, the unit of this would be per unit volume. So this would be volume. So KL times A prime times X over rho cell would be the for a particular given volume. So this would be the mass transfer coefficient times the difference, of course, S0 minus S. So this is the amount of substrate transport. Why is it proportional to X? Why is it proportional to X? Because the more is the volume of the cell, more is the total transport going to be, right? And the volume of the cell is proportional to its weight. Is it clear? The more is the volume of the cell, the more is the total transport going to be. Is there something you agree with? Okay. So next is this is the rate of substrate transport, and then what is it that we are going to balance it with? What is going to happen? So at the interface, for example, this is the rate of substrate transport at the interface. So at the interface, for example, if there are no internal mass transfer gradients inside the cell, okay, it's very likely that there are internal mass transfer gradients inside the cell, and we did this in another course at some point of time. If some of you did that course, you know that what happens, we solve for the concentration profile within the cytoplasm. You can even solve for concentration profiles of certain materials or substrates within the cytoplasm. It's possible. But here we assume the cell to be very small, and we assume that the reaction within the cell is more or less uniform. We do not assume a mass transfer gradient within the cell, which is not an unreasonable assumption, let me tell you. Okay, it's possible to go, see, you decide what is the level of details you want to go in. So you can look at, for example, if you want to, this model that we are solving, if you want to solve a really detailed model, what would you do? You take the liquid film, okay, and then solve for the profile within the liquid film, solve for the profile within the cell, and then balance all of that. Okay, what we are doing instead is that we are not solving for any of the profile either within the cell or the profile within the liquid film. We are simply saying that the rate of substrate transport is mass transfer coefficient times volume of the cell times S0 minus S. Okay, and for the cell, what is the uptake? So the uptake is due to the reaction in the cell, right? So what would the uptake be? We already did that, the growth. What is the uptake? We did the growth model. So if we are using a monod model, for example, here, what would be the uptake? The uptake is, what I gave here, so which is S times X divided by Ks plus X times Q max. So Q times X is exactly the monod growth model, if you remember. Okay. So I use mu, instead of mu, I use Q over here, and I'll come to the reason of it in a moment. You'll see why I use that. But the same thing exactly. So Q times X. So Q is the growth rate per unit weight of the cell. Fine. Growth rate per unit cell times the number of cell again, because more is the amount of cell, the more is the growth. Is it clear? Linearly dependent on cell. So Q is given as Q max S over Ks plus S, monod growth model, times X. So what happens is that at steady state, these two should balance each other. So this is my basic equation that you have. Q max Sx divided by Ks plus X equals KLA prime X over O cell times S minus S naught. Done? Okay. So this is your basic equation, and what it entails is that the rate of substrate transport at steady state equals the rate of reactive uptake by the cell. Okay. Now, so here Q is, just as we mentioned here, Q is Q max S over Ks plus S. Okay. So what we do here is that we express S as a function of Q. Okay. So we express S as a function of Q. Why do we do that? I'll come to that. It's written here. So once you do that, you express S, so S becomes Q times Ks over Q max minus Q. Once you do that, what you can do is look at this equation. You can go and put back your S here in terms of all other variables. Then this becomes an equation in S naught, and you can solve for S naught straight away. Okay. And this becomes a linear equation in S naught. So you can solve for S naught straight away, and this is what you get for S naught. So S naught is now expressed in terms of different transport properties and Q. So Q is a variable, remember, but everything else is a constant out here. I will see in a minute why I'm trying to do that, Okay. Now what I do is, now this new thing comes in over here, is that I define the yield of X per units S. Okay. See, here when we are writing a balance, let's see, when you are writing a balance, you are writing a balance for the substrate. Okay, remember, you're not writing a balance for the cell, you're writing a balance for the substrate, and that's why I used a Q over here. Now if I'm doing it for, if I want to convert it into the cell, the yield of cell, so when you did that's the only little bit difference between what we did with the monod growth model and here. Monod growth model was quantifying the amount of cell growth, okay, and therefore it was given as mu times S, mu times X, whereas this one quantifies the amount of substrate uptake. Okay, and Y is the one that gives the yield of X per unit S. What does it mean? That, see, it's not necessary that there is to be a 1:1 relationship between the uptake of the substrate and the production of the cell. It's not necessary that 1 mole of the substrate should produce 1 mole of the cell. So mu is that ratio. It could be that 2 moles of the substrate produce 1 moles of cell. So Y is the ratio that would be that. So mu over Q. Okay, so Y could be half, Y could be 0.3, 0.4, Y could be 2 or 3 even, unlikely, but it could be 2 or 3. But you understand the concept very, very clearly. Should I explain one more time? So what happens is that when I wrote this equation, I use Q because Q was for the substrate, whereas when you use these notations, you have to remember. So when you use it for the cell, it's mu, and when you use it for the substrate, it's Q. Okay, and mu over Q is the amount of cell produced, amount of X produced per unit amount of S that comes in. Okay, is it clear? Okay, so now I can write the same equation in terms of mu How do I do that? See, for example, so Q is mu over y, right? From this equation here, look. So y is mu over Q. Therefore, Q itself is mu over y, right? So we substitute that. Okay. So then let me use the pen here and I'll explain. So S naught here, Q Ks, Q max minus Q plus. So y being mu over Q, which means that Q itself is mu over y. So S naught then becomes mu over y times Ks. Y is a number, remember, it's not a variable, just a number. Okay. 1 over y mu max. Okay. So 1 over y cancels out over here. So you have mu Ks divided by mu max minus mu plus mu rho cell y KL prime. Okay. So if I go back to the screen now, so the last thing you see is exactly what I did just now. So mu Ks over mu max minus mu plus mu rho cell over KLA prime y, right? Okay. So, so if you look at this equation that you get over here, you can solve for mu in this equation. Okay. You can solve for mu in this equation, provided, because mu is a variable. Now Q earlier, so what we did was, what did we do essentially? It was a variable. If you put your S over there, then it was a variable in S, but we didn't want to put our S in there. So we put it in terms of Q. Then we converted Q to mu. Okay. And then you can solve for mu, because mu is a variable which is unknown over here. And that could be solved for if the determinant is greater than 0. Right? You may want to take a minute and look at this, or if you want, I can show you this. Maybe that's what I will do. So here, so your equation is mu Ks mu max minus mu plus mu rho cell KL A prime y. Then you multiply the whole thing by mu max minus mu and so on. So you get mu max minus mu times KL A prime y equals mu Ks KL A prime y plus mu rho cell mu max minus mu, right? So this becomes a quadratic in mu. So this, if you take it, so you get mu square times rho cell plus, let's see, so minus, sorry, so minus S naught KL y plus Ks KL A prime y plus rho cell mu max times mu plus S naught mu max KL A prime y equals 0. Right? So this is your quadratic, and so all you need to do is look at the determinant of this. So this is what I do over here, and for this to have a solution for the equation that I just wrote, the quadratic equation, for that to have a solution, the determinant has to be greater than 0, which is what we use. Why are we trying to do this? See, what were we trying? Do you have a sense why are we trying to do this? This looks too complicated mathematically, but physically, what are we trying to aim at, or what are we trying to find over here? Yeah, minimum concentration of what? Yeah, so initials, S naught is a initial amount of substrate that is there, and what is my initial amount of substrate that I require for the cells to grow, because that is very important. We need to figure out, see, if you undernourish the cells, they are never going to grow. So what we are going to find out is that what is the minimum amount of substrate that is required for the cells to grow. See, we had the equations long back. If you look at what is here on the screen, see, we had the equation right here, and what we could have done is straightforward gone and solve for S, right? This is a quadratic equation in S. We have it, and you can go and straightforward solve it and get a solution. But we didn't go that way. We went another route, and the reason was it is more important to actually find out that what is the minimum amount of initial substrate that you need to nourish the cells experimentally for experimental growth, rather than to actually solve for what your substrate amount is. So that is exactly what we are trying to do. We can always solve that, and that's not a big deal to solve that quadratic equation. But what we're trying to find out is what is my minimum amount of substrate, and how do you get that? You get that straight from this equation, fine? Because everything else, as you see over here, mu max, rho cell, KL, Y, and Ks, these are all constants. So the only unknown over here, or thing that you want to control rather, so these are things that you cannot control. Mu max is a property of the cell you cannot control. Rho cell is a property of the cell you cannot control. KL again is a property of the cell and the substrate and liquid in the cell you cannot control. Y is the property of the cell and the substrate you cannot control. So these are things you cannot control. The only thing controlling parameter that you have here is S naught. So what you want to do from here is that equate this, so you put for S naught this equals 0 and solve for S naught to get what that would give you the minimum amount of substrate that is required for the growth and nourishment, and therefore the growth of the cells. Is it clear to all of you? Okay. So then once you do that, so you can once this condition is satisfied, then mu that you had over there in the equation itself could be written in this form. What am I trying to do over here is that what am I trying to do? Do you have a sense? So this part, is it clear? So this is separate from what I have in the below. Don't worry about this. Is that up to that? Is that clear to everybody? The S naught thing, that what we do is figure out what is the minimum amount of substrate that is necessary. Now this is something different I'm trying to do here. What am I trying to do here is, see, my model that I have over here, this one, is a model for the monod growth, okay, but the actual growth that is taking place is not the monod growth. Why? Because it's limited by mass transfer, because it's limited by transport, and therefore the actual growth is not the same as the monod growth. Okay, so what I'm trying to do is trying to find out that what is my actual growth, and that there's a little bit of algebra that is here, and you can have a look at that when you go back home. Is that you convert this, so S you can. What do you do is that what is the difference? So if I had monod growth, for example, let's see, what would be my growth if I had monod growth for the cells? This is for the cell, okay, monod growth. You simply have mu max S times S naught times Ks plus S naught, right? And of course multiplied by X, that is always there. But so your mu monod, let's call this mu monod, is this, and your growth rate dx dt would be mu times X, right? Now in the presence of mass transfer, how is this going to alter? What is the growth rate going to be in terms of presence of mass transfer? This is going to be mu, let's call this mu monod, so mu m times X. Now this is going to be mu something else. Let's call this mu mt times X. Okay. How is it going to be different? Mu mt equals what? It still follows the same thing. What is mu mt? Times S plus Ks plus S. Okay. We did that before. Here. Shouldn't look so. This is the one. Okay. So what's the difference? The difference is, for pure monod growth, if there is no mass transfer, it will be S naught, but in the presence of mass transfer, you have S. And what you need to do is, you simply need to substitute for S. How do you substitute? If you let's look at the screen here. So this is my equation. Now that I have figured out what my major first motivation was to figure out what is the amount of minimum amount of nutrients that are required. Once I have figured that out, I go ahead and simply solve for the S, which is a quadratic equation. I'll have two solutions. One would be unfeasible solution, one would be a feasible solution. Take that solution and then I can put it back into, let's look here. So I put it back, so I get the solution and I put it back over here. So so now my S, that the solution S that I get is S naught plus, I'm sorry, that's not the thing that you get. Yeah, I think what will happen is, it's a little bit of algebra out there, so I'm skipping the steps. You can just go and check. You will get mu max S naught Ks plus S naught plus mu max rho cell plus KL A prime into Y. So this is what you get, and okay, so this is what you get. So the algebra out here is that you'll have a denominator, it will get cancelled. A little bit of algebra is out there once you solve for the S naught. So what you need to do is go back, solve for S. So take the quadratic equation, solve for S in terms of S naught. Okay, if I need to explain, I'll do it one more. I think I have it here. Yeah. So this was no, sorry, this is not the quadratic equation. Let me write down, if K, I don't want confusion in this. So mu max S mu max times S times X over Y Ks plus S equals KL prime A X over rho cell S naught minus S. So this is your quadratic equation that you now need to solve for S. Okay, is it clear? Solve for S using this quadratic equation, and the solution that you get, put it in mu. So mu equals, or mu mt, let's say, equals mu max S over Ks plus S. Put that solution that you get into this. Okay, what you will get is mu max S naught Ks plus mu max rho cell KL A prime Y plus S naught. Okay, this is what you will get. So solve for S, put this into this, and after a little bit of algebra, there's some denominators which will get cancelled and some things will happen, and this is what you get. Now what we're going to do is, how does this look? This looks similar to the monod model if you look at it, except that if you call this K apparent. Okay, if you call this K apparent, then this simply becomes mu max S naught K apparent plus S naught. Fine. So this again looks like the monod growth model, but with a difference. Now let's go to the screen. So this is my K apparent. So if you want to write if you didn't write what I wrote, this is what it is. So mu mt is mu max S naught over Ks plus S naught plus this term, so which could be written in the monod form, mu max S naught over K apparent plus S naught, where K apparent is Ks plus S. So what it means is that Ks, because this term, mu max rho cell over KL Y, which is larger than 0, of course, greater than 0, which means that K apparent is larger than Ks, which means that the overall growth process is slowed down, which is obvious. If you have mass transfer resistance, the overall growth process is obviously going to be slowed down. Okay. Excuse me. So in the absence of mass transfer, my mu m was mu max times S naught over Ks plus S, and in the presence of growth transfer, my mu m is going to be small, mu mt is going to be smaller than mu m, or in other words, the new growth rate, or the specific growth rate, mu is called the specific growth rate, the new specific growth rate is going to be smaller than the old specific growth rate. Right? Is there any question on this, anybody? Okay. So just, is that fine with everybody? Okay. So then we will move on to the next part, that we'll do today is the growth of fungi. Okay, slightly different from the growth of the cell. The reason the fungi is different from the growth of cell, and you probably know this, is that you've seen fungi growing in trees, right? You've seen how fungi grow in trees, and this mushroom-like structures they sometimes form. So, what is the major difference that in the way the cell grows from that a fungi will grow? The major difference is that the cells, though grow along each other, with each other, but they are separated from each other within the in the cell growth chamber. So, if I'm to draw the process here, so take something like this, and then one cell will grow. You start with one cell, for example, and then you have 2 cell, 4 cell, and so on. This is going to continue, say, but it grows like this. So you have the medium out here. Okay, so the medium is out here all over. That is why we could do a model like this, where we took the cell and we took the medium around it. This is the cell growth, general cell, normal microbial cell growth, and fungi growth is different in the sense that again you can start with one cell, but they grow in colonies. There is no medium around. The only medium you have is outside the colonies. Okay, so they grow like this. Now, can you this is an interesting question I want to ask you, is that can you tell me from an evolutionary perspective that which one is better, which kind of growth is better? So you have this growth as a, so there is no way you can take this. So if you have to take this, you have to take the whole thing together as a colony. So whereas you can isolate a single cell over here, but you cannot isolate a single cell over here. You have to, it grows like a colony. So tumors also grow like that in colonies. So from an evolutionary perspective, can you tell me that which one makes more sense? Which one is better from an evolutionary perspective? Okay, I'll give you the answer in a way almost that. Yeah. So what is the answer to my question? Which is better from evolutionary perspective? Which kind of growth? Better, right? That's correct. So the single cell growth is better from an evolutionary perspective than the fungal growth. The reason, and the answer is there almost, that the cell growth includes all kinds of cell growth, including human cell growth. So this cell growth that we're talking of course more evolved species. So all kinds of cells, whereas fungus is a lot more primitive species. Okay, and much of earlier cell growth actually started like fungal growth. So fungus is a lot more primitive species than cells, normal cells, and normal cells is a more evolved species, and the whole of evolution more or less is put towards getting towards a more intelligent, creating more intelligent cells and species. So that is why human beings think that they are the most evolved, because they were the last formed, the last species formed. So if there is another species formed after human beings, they'll be more evolved, because evolution always works along the path of intelligence. So whatever is a more intelligent, self-sustaining process, they will work towards that. So what is the major difference between this cell growth that you see over here and the fungal growth is what he just Kaushik just mentioned, is this mass transfer resistance is a lot lesser here as compared to here, because you have fluid around it. So which means that nutrients can enter each and every cell. For each and every cell, nutrient is made available. Whereas what happens is that there is a hierarchy almost here, that in a fungal growth, first the outside cell, the cells near the border should have nutrients, and they should grow. Only after they have eaten, they will pass on what is left to the one that is inside. So both mass transfer resistance are both here and there. It's a lot more over here actually, and so from a sustainability point of view, nutrient sustainability point of view, what happens is that the accessibility of nutrients to the species inside, to the cells inside, is a lot less than the accessibility of nutrients to the species outside, right? So that's an evolutionary perspective. From a simple chemical engineering point of view, we can kind of sort of trivialize it almost and say that the surface area for mass transfer that is available is more when a single cell is there as compared to the surface area of mass transfer when a colony of cells. But I wouldn't go to that level because, as I said, that would be almost trivializing a process that is as complicated and as grand and as evolutionary as this one. So the basic thing about fungal growth is something that I just discussed, is that it grows at a as a colony, as a mold colony. Okay, so here as I write, so it grows as a mold colony, and it shows a constant rate of increase of radius. And you know, this happens whenever some species, anything grows as a colony. For example, the question I gave you in the test was about this growth of tumor, and tumor also grows as a mold. Okay, like a mold. So it grows together as a colony, and therefore this shows a constant rate of increase of the radius. Okay. So anything that grows as a mold or a colony shows a constant rate of growth as a radius, constant rate of increase of radius. The reason being that, you know, why? Because see, it's that total amount of nutrient that is entering the system is a constant. Okay. So it's not a single cell. It's sorry, it is all the cells together are acting like a single cell over here, right? So that's the major difference. So whatever nutrient is available to the whole colony of cells. Okay, and then there is a gradient within it, and we'll look at the gradient, what happens and so on. So if you have dr dt, which is the rate of increase of the radius with time, that equals k, a constant, and at any instant t, k is a constant here, because that's what happens in the fungal growth. The radial no, we're talking about single mold over here. It's not a mold that is not breaking. A single colony of cells that is growing. See, there is a process. It can break only after it has reached a threshold. It's not that every fungus will lead to another to fungus. It will reach what happens is the mold will reach a certain threshold of radius beyond which it cannot take itself, and then it will break. And I'll also come to what is that threshold. Okay, I'll show you that. So this is the process where the fungus itself is growing as a mold. A single fungus is growing as a mold, and the rate of increase of radius is a constant over here. And so we consider here in this problem that we do today, we consider a cylindrical mold. Okay, so if you have a cylindrical mold, then the x is pi r square over h times rho. Okay, so this is the radius at each point of time, which is increasing. This is the height of the mold, and rho equals the density. Fine. So this is what you have. Now dx dt would therefore be, since the height is not increasing, dx dt would simply depend on the increase of the radius of the mold. Fine. So this is what we do. We differentiate both sides of the problem. So you get 2 pi rh rho times dr dt. Fine. Now what are we trying to do over here next? What we're trying to do is simply express everything in terms of x. See, when we did the last model, we had everything in terms of x. So we want the growth rate not in terms of the radius, but in terms of the cell itself. So dx dt, then what you do is simply replace your r over here by square root of x that you get here. So from this equation, right? So, and then you'll get this. Okay, let me show it here if there's any confusion. So x is equals pi r square rho h. So dx dt is 2 pi r dr dt times h rho. Now from here what I get is that r equals x over pi h rho square root of that, and I know that dr dt equals k, so I put that over here. I get dx dt equals 2 pi square root of x over pi h rho times k, which leads to times k, right? So then you can simply go ahead and integrate this, and you will find out how the mold changes with time. Okay. So you assume that at the start the mold had a total weight of x naught or something, and then you can just quickly go and integrate it, and then you will get x as a function of time and x naught. A straightforward integration. Right? That? Okay. Now what we look at is the same problem, but we're now looking at a spherical mold, and so some fungi will grow as cylindrical, some as spherical. So again, you can repeat the same steps. So x equals 4/3 pi r cubed rho. So dx dt would be 4 pi r square dr dt rho, and then you can replace again r from that, and then you, instead of half, you'll get a 2/3 over here, which you can again integrate. So once you integrate, this is what you get. X equals some gamma t times over 3 plus x naught to the 1/3 whole cubed. So what was your expression for the spherical mold? It was some lambda t times something squared, and this one you get gamma t times cube. So which means that a spherical mold will grow much faster than a cylindrical mold. Right? Goes as cube of time, and that goes as square of time. K. You got K, dr dt as constant, right, to start with. That was the assumption. It's not a strictly valid assumption, but sort of reasonably valid assumption. Once you're done, just let me know. Finished? Okay. Now comes the question that, if, just like we did for the for the growth of the for enzymatic reactions, then we did the same thing for normal cellular growth. Is first we looked at the aspect of growth, the reactive aspect, and then we looked at the mass transfer aspect. So same thing we are going to look at exactly now. That is, look at the effect of mass transfer, and that will partly answer your question about the threshold and which is the point that it can keep growing. So when it cannot keep growing any further, it will break into two to reduce. So that's again an evolutionary thing, to reduce the amount of mass transfer resistance that is offered to it. Okay, so that is what we're going to look at now. So excuse me. So this is a cylindrical model that we are taking, so cylindrical fungal palette. Let me just go back. So this is what we did for the growth process, but this growth process that we are talking of is not a complete growth process. The reason being that there is mass transfer resistance that is offered to the substrates. Okay, so because the substrate can only reach the outside, so that is a major difference from here, as I explained, to with major difference between this and the single cell model. So this is a substrate. I refer to that as an oxygen, but it doesn't have to be oxygen. It should be everything else: oxygen, carbon dioxide, carbon, hydrogen, everything put together. Let's say. So, but let's assume it to be oxygen. So this is the equation in dimensionless form, and the reason I wrote it this way is that you can go back, and we did this already for the enzymes, and you can go back and look at the dimensionless form for the immobilized enzyme. If you remember, just before the exams, we showed how to make it dimensionless for the immobilized enzymes, and exactly the same thing. And so beta, so these are all these the same coefficients that we had before, and this has to do with the Michaelis-Menten kinetics over there. So this is the dimensionless form. What if you don't trust this form completely, then you can go and derive it from what you had. But the reason I'm not repeating is because we had already done this in the immobilized enzyme part. Okay, so 1 over r. So r bar, this is r bar, is the dimensionless form of r. And how do you make it dimensionless? Just make it dimensionless with some initial radius, because the radius is growing. Okay, so just make it dimensionless with some initial radius. So r bar times dc dr times, this is the reaction. So what is happening is that this is the diffusion that is occurring of the substrate inside the mold, and there is reaction that is occurring. So, couple of things that we need to understand this, before we go further with this. One is that as in the cell, while in the cell we neglected the gradient, mass transfer gradient of the substrate within the cell, if you remember, but we cannot do it here. Okay, why is that? Because the cell is much smaller entity. So what we did here when we did the cell example was, and this is the fungal model, so we neglected the mass transfer gradient, neglected MT in cell. We cannot neglect MT in cell, because the length scales are much larger here, so the diffusional gradients are going to be much larger over here. Second is that this is A, cannot neglect mass transfer resistance in fungal pellet. And B, let's go back to the screen over here. Okay, what you see is a steady state. This is the question I have for you. What you see is a steady state equation, but the fungal pellet is growing. So where is unsteady term? Why is there no unsteady term over here? There should be, right? Fungal pellet is growing, so you should have the whole process is steady. So what is happening here? Why do we assume steady state? We're running out of time today, but I'll just explain quickly why. What we do is, let me write it here. Assume, this is a very important thing, and maybe I'll start tomorrow's next class with this, quasi steady state. Again, this may be a new concept that you are dealing with today. So this is different from assumption of quasi steady state in the enzymatic case. Please understand. What is happening is that there is an unsteady process that is happening. Okay, that is the growth of the fungus, and there is probably another unsteady process, which is the diffusion of oxygen into the cell. Now, whenever there are a couple of processes, 2 or 3 processes, and we want to make some assumptions about one of these processes, what do? We compare the time scales of these processes. Fine. So what are the time scales over here? How do we compare the time scales? One is the time scale of growth, fungal growth, TG, let's call it. The other is the time scale of diffusion of the oxygen. So what is the time scale for diffusion? Let us assume that at any point of time, at a certain point of time, at T equals T naught, R equals R naught. That is at T equals T naught, R equals R naught. That is the radius of the fungal pellet. is some value. We need to assume some value, otherwise we cannot do radius of fungal pellet. So what would be my diffusion time scale? R naught square by D effective. Fine. What would be my growth time scale? What would be my growth? So the fungus is growing in general, right? The radius of the fungus is increasing. So what would be my growth time scale? We had it in the last example we did. You just have to use that. What was dr dt? K. So what would be my growth time scale? So Tg would be not into R naught over K. Okay. R naught over K. Right. So if you have to assume quasi steady state, what quasi steady state of what? What does a quasi steady state means? Quasi steady state that you have assumed, if I go, let me go back to the screen here. What it means is that, what quasi steady state means is that I wrote a steady state equation for the diffusion of oxygen, but I am writing unsteady state equation for the growth of the pellet, for the growth of the radius of the pellet, which means that the diffusion of oxygen is much faster than the growth of the radius movement of the radius of the pellet. The radius of the pellet, the fungus radius, and this is not true, in real life. The fungus radius, it doesn't change every second. It changes over a period of days, whereas oxygen diffusion is taking place over time scales of minutes. Is it clear to all of you? So what I need is that the diffusion time scale Td, what is the relation between the diffusion time scale and the growth time scale, and Tg over here, what would be the relation? Td should be much greater. Time scale should be much smaller than Tg. So Td should be much smaller than Tg. That is my requirement, which means that if I put Td should be much smaller than Tg, which means R naught over K should be, sorry, not R naught over K, R naught over D effect, R naught square over D effective should be much smaller than R naught over K, okay, which means that R naught should be, R naught over D effective should be much smaller than 1 over K, okay, or K should be much greater than D effective over R naught. Fine. Okay. So this is the criteria that we need for quasi steady state to be valid. If quasi steady state is valid, then we can go ahead and write this. If quasi steady state is not valid, then what do you do? Then you have to write dCO dt, del CO del T, sorry, plus 1 over R del R of R del CO2 del R equals some CO2 CO times mu over K 1 plus beta CO. So we'll stop here today. We've run out of time, and we'll continue from here in the next class.